Hello, I'm Keegan Williams, and this is my Physics 2211 lab on oscillations. So to first understand this lab, we have to know some fundamental physics principles, including the momentum principle. So the momentum principle states that an object's momentum will change over time when a net force is present, and this can be rearranged to get the position update and velocity update equations, which will be implemented in the GlowScript codes. We're also going to be using the energy principle throughout this experiment, which will involve gravitational potential energy, spring potential energy, and kinetic energy. And below you can see all the relevant equations we're going to be using throughout this lab. So the purpose of this lab is to see how the energy principle is utilized in complex systems where the force and energy can change over time. By using a computer model, we can effectively predict the motion and energy of an oscillating spring mass system given initial conditions. So through this lab, we will see that the model is an effective indicator of the motion of the mass on the oscillating spring. We will also see that the model was more effective in accurately predicting the motion in the x direction rather than the y direction, which is likely because there was less forces acting to influence the motion in the x direction. Here's our tracker video, which shows the spring mass system. So to better understand this experiment, we can define the system and draw a free body diagram. So the system for this experiment would be the hanging mass in the spring, which means that everything else is the surroundings. After the mass is released, the net force will change as the spring force changes. So although the video was borrowed and pre-recorded to perform this experiment, we would first have to fix a spring to a fixed point and attach a mass to the end of the spring to create a system. So additionally, we would need to measure the hanging mass, the length of the spring before and after the hanging mass was attached, and the initial position of the spring before it was released. In this experiment, we assumed that the spring has an initial velocity of 0 meters per second. After obtaining a video, we uploaded the data to Tracker, where we hand-placed coordinates over the position of the mass as it oscillated. Then, using the Tracker position data in GlowScript, we compared our experimental data to a computer model that assumes ideal conditions. So for implementing the code in writing our initial conditions, we first had to find the mass, spring stiffness, relaxed length, and the starting point, along with the initial velocity, from the week 8 pre-lecture videos. Below you can see where we implemented these in GlowScript. Additionally, you can see where we calculated the initial system energies using the fundamental physics principles described earlier. And in the bottom right corner, you can see where we implemented the system energies. So as for the momentum principle and energy changes throughout the iterations, the net force is equal to the force of gravity plus the spring force, as shown. To find the new velocity and position for every iteration, we can use a velocity and position update formula, which requires an understanding of the momentum principle. Additionally, every time step updates the spring displacement. So the energy values are recalculated using the new velocity, position, and spring displacement, which will be reflected in our energy versus time graph in the next slide. So this is our energy versus time graph, and as you can see, delta E is 0, which means that energy is conserved. So here's the differences between our observed and model position versus time graphs in each direction. And you can see that the y position versus time graph is slightly more inaccurate than the x position versus time graph. So yeah, the x position data is more accurate than the y position data, and this is mostly attributed to having less forces interacting in that direction. Also, the model slightly overpredicted the position of the mass, which can be explained by sources of error that include the non-ideal spring. Additionally, more possible sources of error would include the video's description of the system in the pre-lecture video may be slightly inaccurate, the hand placement of the positions, which may cause our experimental curve to be inaccurate, small forces that could have affected the system, like the drag force, and the delta t, which is derived from trial and error. So follow-up questions. So is the energy principle satisfied? Yes. Since delta E, or the total change in energy, is 0, this indicates that the energy was conserved throughout the entire experiment. This means that delta E equals delta K plus delta U grav plus delta U spring equals 0. Since this is a closed system, energy is never lost in the model. Instead, energy is transferred from one form to another, such as kinetic to spring potential, or spring potential to gravitational potential. So, using our information, we can compare the oscillation and derive the oscillation periods for the x position and y position data. So, to do this, I recorded the time at 2 consecutive crests and found the difference in time, which will give us one period. In the x direction, I found the period to be 1.6 seconds. In the y direction, I found it to be 1.5 seconds. So, in conclusion, this lab was valuable for analyzing and understanding oscillatory systems where the net force and energy vary over time. Using a computer model, we effectively predicted the motion of a mass in an oscillating spring mass system based on its initial conditions. Our results showed that the model closely matched our experimental data, suggesting that while some energy was lost due to the open nature of the system, such as due to friction, air resistance, and other factors, the total energy of the system did not change significantly over time. This finding reinforces the principle of energy of conservation, that energy is never lost, but rather transferred, such as through work done by or on the system.